research, and then I was sharing the passion with the rest of the world. So, and there were 16 countries, included Karachi. Also, I've been to Sir Said University many times.
Oh, so that's good.
So that's what I say to the students. Yeah, go do good work, get into PhD program, do some good science, and you'll see the world for free. Not just free, they'll pay you to go to those places. Search, and then I was sharing. All right, so today we'll continue nanomaterials, especially we'll focus on quantum confinement. So quantum confinement is a concept which relates to the change of electronic and optical properties from the bulk materials, especially when the materials that we are dealing with inorganic, crystalline, and they are of small size. So generally below 10 nanometer is when we see that phenomena, what we call as quantum confinement. So it's nothing but the spatial or the physical confinement of excitons. So excitons is electron hole pairs. We just call them excitons. And it may be one-dimensional, two-dimensional, or three-dimensional. And there's slightly different physics that goes to explain that. And there's lots of work that has been done in last 1-2 decades on quantum confinement, or we generally call them low-dimensional materials, right? Low-dimensional because 3D, we know 3D, right? But 2D, real 2D is a material which has very small thickness, so thin films, but it's spread across the board. And that has opened this experimental research and theoretical research has result into many new capabilities for to make them reproducibly and to control their electronic and optical properties. And when you say control, then we can tune those properties as well. So think about it like we used to have radio, right? So you have to tune to your station. So you get exact frequency that you get. So here it's also related to what we want to get. What we do get is the wavelengths because we are using them. Many of those materials, especially the 3D, the zero-dimensional quantum dots for their optical properties. Now, this 2D, 1D, and zero-dimensional nanomaterials, they have enabled us to use the standard framework of semiconductor materials or semiconductor devices to bridge to these inorganic materials and to use the high performance and the stability of inorganic materials. Now, the properties that we are using is the distinct change of electronic or their optical properties because of confining them, because of making them at nanoscale, because of their being in low dimension or small size, right? So we generally call these as quantum confined structures. And these are distinguishable from amount of confinement we get, right? So 3D where the carriers can go in all directions. Then 2-dimensional would be where it's a very thin film and they can only go in 2 dimension. And when we get to 1D is they have one specific E, plus X or minus X. And then we get to 0-dimensional where they are like, they have nowhere to go. So all what we do is we play with their energies. There's no movement, there's no charge transport, but what we get is interaction of light with the energy states within that 0-dimensional material. Now that energy state interaction gives us very specific wavelength out of those materials. Now, for this topic, I have to be very careful without going into too much physics because it's an introductory lecture. But there are some concepts which we have to revisit, especially when we talk about the optical or electronic transitions of semiconductor materials. We have to think about valence band and conduction band, and then we have to think about how particles, when we say particles, we are dealing with electrons and holes, how they behave when there is an energy state change between them. Now, so that's where we have to look at some physics of semiconductor materials to help us understand quantum confinement. So I bring up here the energy band diagram of a semiconductor material. So energy band diagram, I'll go back to the previous slide. So what it does is, so when we have an electron, or we call them wave particle duality. So you can call a wave, or we can say electron. It's when it's confined in a boundary, it has specific energy levels that it can occupy. So there is a low energy area, we call that valence band, and then there is a forbidden zone that there is no energy states. And then again, there are energy states. So unlike metals, we should say unlike conductors. In conductors, as soon as you switch on the voltage, or as soon as you excite them, the current starts flowing. But in semiconductor materials, you have to excite them with external energy, which can be heat, which can be light, which can be voltage, for them to jump from valence band to conduction band, and then they are ready to travel. Then once they get there, then you get conductivity, right? Then you get charge transport, movement of charge, what we call current by definition. So here there are two important aspects. Number one is that it should have enough energy to jump over the band gap, and then there should be states available, energy states available that it can occupy. So in semiconductor materials, then density of those states is another important factor. How many states are there? So density of states, that's a concept that comes from there. Now, in bulk semiconductors, we have many density of states available. So we don't worry, but we have to still provide enough energy for them to jump above the forbidden zone and get to the conduction band. So far with me on this very basic introduction to band gap and semiconductor devices.
Sir, now, here the meaning of densities means to store, sir.
Say it again.
Sir, the meaning of densities here, sir, to store the something,
no.
Sir.
States, energy states, empty states where an electron can go. You see, there are lower level where all electrons are filled. Then there is a blue place, because from that blue place, that electron is jumped. So when it goes to conduction band, there has to be places where it can occupy. If there is no state, energy state available there, then it has to come back. So states, or it's nothing like if you come on campus and you have to find a parking spot, right? Your car is there, but there's no parking spot, you have to go back. So there are energy states, energy levels that has to be available for electron to occupy and be available for conduction. I'll stay with that because going deeper will become much more device physics. So we need to find out how many states are there. So we use a quantity. So we have an equation that we solve, Schrodinger's equation, to find our density of states. So now this band gap is also essential. So we know how much energy it needs to get to those empty states. And once it gets there, then once it jumps, then it has the energy. Then it fills energy state depending on which level it is. So if all the energy states close to the cutoff the conduction band are filled, then it has to find a state at a higher level. But the idea is that there is a forbidden zone, there is valence band, there's conduction band, but electrons have to jump up to get there. Now, that's 3D. And in 3D material and big materials, the left-hand plot shows that higher energy density of states become constant, saturated. So you have fewer density, fewer states at low energy when energy goes up. But that system breaks down when we physically confine the particles. When I say particle, electrons, when we physically confine the electrons. So what happens is that we have to then apply some approximations in our standard energy calculations. The equations that we, Schrodinger equation, we solve that, right? That's a little bit tricky. If you are into devices, then you would know how to do that. And so because of those approximations, we have to then modify the solution. So when we modify, the band gap changes, the absorption coefficient expressions change, and density of states change. So that helps us understand, and we see this in 2D, we get this ladder type of states, and instead of a continuum of states, we get very discrete levels of states. So this time-dependent Schrodinger equation, which is a specialized field, and all device people know how to do that. In that, then we take care of light and electrons. And the quantum confined systems, those many parameters which we take constant in bulk semiconductors, now they become dependent on the dimension of the material, right? So, and that's why we call it quantum confinement, because now we are making things so small physically that the bulk level approximation or ideas, they have to be adjusted. And that means the band gap, the band edge positions like conduction band and valence band positions and density of states, they all change because of the effect on the transition probability, like electrons jumping and going to the conduction band. So that there is also a probability there also. So these things change. So hence, we have to get a new approximation, and a more important approximation that changes there is an idea called effective mass. So effective mass is now approximated differently when we are doing the general form of equation in finding density of states in the quantum confined structures. Right, so now in a 1D confined system, which is a 2D material, right? So you have to understand when we talk about confinement in a different dimension, but that means a 2D material or a 3D material. So type of material and confinement are two different concepts. So that's why you have to relate the bulk quantum well, quantum wire, and quantum dot. And they all have different confinements. Now, in a 1D confined system, for example, it should be a 2D material, the density of states are affected by the decreased freedom for the charge carrier, right? So they can only do a 2D movement. They don't have a 3-dimensional movement, right? So that shows, when we look at the density of state, that shows instead of a continuum, it shows step kind of thing. So which means between those two levels, there's no state available. So we have adjusted the band gap in a way. It has more discrete levels that are available for electrons to occupy. So this lower figure is just an illustration of the broken symmetry, which you have in a 3D system. And that shows the functional density of states in 1D, 2D, and 3D confined materials. All right. Now, what does it mean? So it means that we can get new type of materials, and we'll focus on quantum dots, which is where they are restricted in all directions, right? So which means that there are only two levels for the density of states, very discrete levels. What does that mean? Which means that they can be tuned by that to emit very specific wavelengths. All right, so let's take a step back from the emission also. So first, what will happen? You have a a system where you have electron in the valence band, we have to excite it somehow, which can happen with many ways. But here what we do, we excite it with external light. So we shine photons, which makes electrons excite and go to valence band. From valence band to conduction band. You remove the excitation, electron has to jump back to the valence band. Now the difference of that energy will be emitted as a photon. So that photon, now these are, if there were multiple density of states, the electron could have come from any different state, which now the energy difference is a direct relation, has a direct relation with the wavelength. E is equal to hf, f being frequency, h being Planck's constant, right? So one constant, E proportional to f. Now when there is only one state, which means it is going to emit only one frequency, one wavelength, right? Which means only one light, monochromatic light. And that's the big goal. And that's what we achieve. But quantum dots are not new. There was research, just like graphene, we talked about that they were talking theoretically for a long time that this can be a system. So theoretical physicists were talking about quantum dots also, confining electrons in 3 dimensions, right? 0D material. So, but now they became available in 90s. So when they ultimately started making these nanoparticles. So they are nanoparticles, they're nanomaterials. What are the conditions? They're crystalline, they are inorganic, and they start showing this optical tuning property below 10 nanometers. All right? That defines quantum dots. Imran, you are with us? All right, yep. All right, so now what is special about them? They have their electronic properties are intermediate to bulk semiconductors, like big semiconductors, and isolated molecules. So if you pick a molecule separate somehow, this shows properties something like that. So although it's a bunch of few atoms coming together, few is probably maybe 100 or 200. So they can show the properties of semiconductor materials, but they are very few, kind of a big molecule. So their optoelectronic properties are determined by how small it is. So the size, their size and their shape. So by changing their size and shape, we can change their optical properties. Now, why it is amazing? It's amazing because at macro scale, large materials, we know every semiconducting material has a very unique constant band gap, which means they can give only the wavelengths equal to their band gap, or some variation because there are other energy states in the conduction band, or they may be traps within the band gap. So they have a range of wavelengths. But now, when we make it small, we can, from the same material, now we can have many, many different wavelengths just because we are adjusting its size. So small variation in size can give us a bigger variation in the wavelength. And for the same material, if you take a big chunk, we don't get this property. So that's the amazing part, that the optoelectronic properties can be tuned at nanoscale by changing its size. Now, if you think about a quantum dot and you think about exciting with the photon of energy with the very specific wavelength, right? F, what we call. So larger size quantum dots would return a different light than the smaller size quantum dots of the same material. Excitation is the same, material is the same, but just because we adjust the size, we get different wavelengths, right? I see a hand. Ahmed, go ahead.
Sir, how does quantum confinement works in nanowire, sir?
Nanowires are 1D. Quantum dots is 0D. It's a different
Sir,
dimension.
so how works, sir, quantum dots work in nanowire, sir?
Nanowire is a different thing. Motorcycle is a different thing. Car is a different thing. Right?
Understand, sir.
Nanowires are something else. Quantum dots are something else. All right?
Okay, sir.
All right. So what we're talking here is we're talking that between 3D, 2D, 1D systems, the nanowires would be what you call quantum wire here. This guy would be quantum wires. When you say nanowire, unless you say that it's an inorganic crystalline material where you have a band gap, then it would be called as quantum wire. Yeah, Habil, go ahead.
Fine, sir. Sir, my question is, we can see the graph of.
You bring mic closer. It's hard to hear. Can you speak a bit?
Sir, can you hear me right now?
Yep.
Okay, sir. So my question is regarding the graphs above, which are the plots above, which are of density of states with respect to energy. So we see spikes for 1D and for 0D. I don't know. These are just 3 lines, or these are some sort of.
Yeah. So you have to. It's just a plot. You have to look at like this: conduction, valence band, conduction band. So energy.
Okay.
Yeah. So yeah, I know what's wrong here. The upper figure is showing energy on y-axis. Sorry, x-axis. The lower one is showing energy on y-axis. So yeah, you have to rotate it. I would say the lower one is more important. It covers both ideas here. Yeah, I shouldn't. Yeah, I'm not. Go ahead.
Sir, in the next slide, I just mentioned that quantum dots are 3D confinement. Sir, why are I get the idea like this. Nanoparticles exhibit 3-dimensional quantum confinements. Like, sir, so it means the quantum dots can move in 3 dimension, right?
No. So it's a ball, very small ball. There's nothing. It's just that. So electrons have to stay in that. There is nowhere for them to go. So 3D confined does not mean they are part of a 3D system. That means, so like this picture, there's just a ball of atoms, and atoms share electrons. So when you excite electrons, they have nowhere to go. All they can do is stay around in those atoms. So what we are doing is we have physically confined them, but we say 3D confined, which means we have confined them from all directions. We have put them on ECL from all 3 directions. They cannot cross land border. They cannot take a flight. They can go out on ship.
So that's why they are 0-dimensional. They cannot move.
That was the idea what I was doing, that confinement from 3-dimensional means a 0-dimensional material.
Okay, sir.
Right? That's why I was highlighting there on some slide that 3D confinement results into a 0D material. Here, this next slide. So you have to understand dimensionality and confinement are opposite, right? So when I say 3D material, it has no confinement. They can go anywhere, right? So 3D material, ups, X, Y, Z, all are open. 2D confined means 2-dimensional. Now they can go in the thin film, they can go around. 2D confined means they can have only 1 dimension, which is nanowire, right? If it's a crystalline material, then it's what you call quantum wire. 3D confined, 0-dimensional material. So 3D confinement and the dimensionality of the material itself are two separate things, but they're related with each other, right? Make sense? So we are using that. Yes, ma'am. All right.
Yes, sir. It
So
makes sense.
we,
Thank you.
right. So we are using, sorry, this is where we are. So we are using that property now to tweak or tune the light that we can get out of them. So we're talking about here that you can have one material, but two different size quantum dots. You excite it with one wavelength, but you will get two different wavelengths from two different sizes. So you excite, which is called absorption, and then emission. I shine a light from outside, which means the nanoparticle, the quantum dot will absorb that wavelength, right? And then it will have an emission of a wavelength. Same material, different sizes, the emission will be different, right? Which means getting two different. Very soon when we see application, then it will help us see the importance of quantum dots or why they are special, right? So now this also means the smaller, okay, different size, different wavelengths, the smaller wavelengths, the smaller size means the different, simply what we say, the smaller quantum dots emit shorter wavelengths because the band gap is smaller, the energy difference is smaller, and E is equal to HF, right? So this is the frequency relationship. So we know exactly then what size would give us what wavelength, or we can tune their size to get the variation in the band gap, which will give us specific material. Now, they are made from 2D, like it is showing gallium arsenide quantum dot, but they can be made by one material as well, like silicon and germanium, or compound semiconductors. We'll look at that. All right. So, excitons, electron hole pairs. So when we create electron hole pair, there is electron that jumps to conduction band, leaves behind a hole, right? So when it comes back, we say exciton is generated and an exciton is destroyed, if you may call it. Now, these are semiconductors, they're nanoparticles, very small, their electronic properties are governed by quantum confinement. So again, quantum mechanics, these equations are different from bulk materials. Now, since we are now playing with their size, they also call them artificial atoms also, because natural atoms, they have their specific constant qualities. But here we are we are using a bunch of atoms now to create, just based on their size, new properties. So we call them artificial atoms also because they are showing discrete electronic states which do not exist in nature, right? So we are, because of their size manipulation, let me see, there are some messages in chat also. Specs, okay, I'm just saying, can I repeat? So when I say so quantum dots are nanoparticles, right? Nanoparticles, small, less than 10 nanometer. They're crystalline. They can be made of binary materials or single material like silicon or germanium. And we can tweak their optical properties by playing with their size, right? So we call them artificial atoms because the properties we are creating, the optical and electronic properties, they don't exist in nature because we are manipulating their size. All right. And we call them quantum dots because we are using the quantum confinement, which results into band gap adjustment. And band gap is nothing but the energy jump that it takes to get excited and to create excitons and that energy that it has to release, the electron has to release to come back to valence band, right? So they are small semiconductor crystals in nano size range, and we call them nanomaterial because of their size, right? But nanomaterial which are semiconductor crystals, nanocrystals, right? All right, so what happens? The electrons jump from conduction band to valence band, and that difference results into emission of a very specific wavelength. Because of their properties, where we can adjust their size and have very unique light, we use them in solar cells, LEDs, transistors, displays, digital displays, laser diodes, quantum computing as well now, and foremost medical imaging, biomedical imaging, right? And the simple reason, this coating on one quantum dot, which will have a very specific wavelength, we can coat them to target specific disease cells or specific biomarkers. And if you can image them, that would mean that disease is present. So there have been many different applications that have been shown, right? Now, the absorption and emission, they can occur at very specific wavelengths, but they are different wavelengths, right? They don't have to be exactly the same. But this one is showing that when you decrease the size, the band gap increases, right? And then when it jumps, that has direct relation to the wavelength that comes out, right? Any questions so far on the very basics of quantum dots?
Sir, according to this diagram, as the size is decreasing, the energy band gap increases. Is that true?
Right. So frequency goes up. H is equal to what was that? E is equal to HF, right? And F is reciprocal of wavelength.
Yeah.
Size goes down, wavelength goes down.
Yeah.
Size goes down, energy goes up, frequency goes up, wavelength goes down. Make sense?
Yes, sir.
So as long as we have these three separate relationships in front of us, we can directly see size goes down, wavelength goes down. Frequency goes up because energy goes up.
Goes up. So it means when we have to excite the quantum dots, we will be needing more energy.
We would need, for smaller one, we need energy that can make them jump the bigger band gap.
Yes.
Right? Now, there's another interesting thing. So you need, yeah, thanks. So let me turn on my annotations. Another interest. All right, what's good now? All right, there's another important thing to note here. All right, Sharam, go ahead.
Sir, how are they used electronically? I mean, we did talk about its optical properties. I mean, in terms of electrically, how are we using it?
Yeah, it's when you talk about quantum dots, we are interested in optical applications. But when we talk about solar cells, you need to capture the light that comes out of them, right? That solar cell. You have to capture excitons that come out of quantum dot, and that is their electronic application. Right? I'll give you an example. Let me show you something, another interesting thing, which is evident, but so to excite them, for example, for this case, you need minimum this energy, right? So you need to get it from here to here, from the edge of valence band to the edge of conduction band, right? So far, makes sense. Let me get a different color. Maybe. Now you can also use higher energy, which can take it from here to here, right? So higher energy, higher frequency, smaller wavelength. So you can have a range of wavelengths to excite it. But what you're going to get is just the wavelengths from here to here. So you may be exciting, we may be exciting with a range of different wavelengths, but what we get would be always going to be very specific for that that size.
Sir?
Yeah.
Sir, can these material energy band gaps dependent on temperature, sir?
So wavelength dependent on temperature.
Yeah, energy band gaps, sir.
Okay. Just note it down. Energy band gap is a constant for any crystalline material. Constant. What happens when you go to less than 10 nanometer for these materials, we are changing the band gap. That's it. Only size effect. All right. There are approximations, there are wavelengths. Yes, there are other things, lots of studies on that, but predominantly quantum dots, where we tune the wavelengths by tuning the size. All right, that's it. All right. So let's see a few applications. Biological tagging. So what's shown here is a quantum dot, right? And we can functionalize it. What this particular example is showing, we have functionalized it with a DNA chain. So now we know what chain it is, and we are looking for a specific target molecule, a specific gene, for example, like we were talking about in DNA microarrays. The binding can result into change in light because of the closeness, or because of maybe binding there with the target molecule. So quantum dots would otherwise wash away, but because they have the target there, so that would show you light, which will tell you, okay, this target is there. We can use it to look for specific protein targets. Then we would know antigen and antibodies, right? So we know they bind. Or we can use it to carry something with a molecule that gets attached to surface receptors on a cell, which would then tell you, okay, that specific antibody or that specific molecule was there. So now, and there are many variations of this basic concept, but the idea is we take the quantum dots, we functionalize them with our biomolecule, knowing what we are targeting, and then we send it in. If they bind, that tells us the presence of light, then tells us that specific target molecule is there. So we can make assays, we can make microarrays with that, we can label cells, we can do imaging inside living things, animals, human even. And we can detect the presence of specific molecules like pathogens or toxins, right? So this is one example. And there are gazillions of examples. I'm just showing you one example where they used quantum dots of different sizes and they functionalized them to go and bind to different organisms, looking for different things, different targets. And once they got that, then you can see in one go, from one solution of quantum dots having different sizes, now they have been separated out, and you can exactly see, because before sending those quantum dots in, I know I put this molecule on the green ones, I put this one on the yellow ones, I put this one on the red ones. If they bind, that tells me those specific biomolecules are there. And those biomolecules may be indicative of a disease. They may be indicative of some function of the body. Observe what's meant by assay. Assay is putting a bunch of molecules and looking for specific targets in one go. So when we assay something, it's a bioterm. We are basically putting the receptors, putting the probe molecules, and we run our sample and we are seeing if there is binding. So that will tell us if those specific things were there in the solution or not. Right? Yeah, Habil, go ahead.
Sir, my question was from, I think, 2 slides back, that when you said that we will get a specific photon of light from for a typical band gap, is it because of even though we can get electron excited to the higher energy levels in conduction band, but is it because that electron de-excites to the conduction band edge?
Yeah,
That's why
it
we do get a
loses,
specific.
right. So it loses energy, and we know now there are very specific density of states in a quantum dot. It's going to get to only those states. There is no more state for it to go, right? So we can make it jump with higher energy, but it has no way to go except these very specific density of states in conduction band, right? So we can excite it, but it's going to emit only one wavelength, right? So what are those wavelengths? How do we deal with this? Okay, this is the most, yeah, they're all amazing. I just say, I like to highlight this one. So look at this one. What's the y-axis? See the difference. How much is the difference in y-axis? From 4 to 6 nanometer, right? This is 4. Oh, hold on. Let me see. Let me turn on my annotation so we can see it better.
3.5 to 6.
So if I say going from here to here, right? So this is 4 nanometers and this is 6 nanometers, right? So the change in size is how much? 50%, right? 4 to 6. What's the change in frequency here? So if I draw the line, bring you all the way down, how much is the change in the wavelength? Huge, right? With respect to size, you are going now from 900 to what, 1250? A big wavelength difference, just by 2 nanometer size difference. So gives you unlimited capabilities of wavelengths with just slight change in their size. I don't know if you feel the excitement that I can see here, that just this tweaking of a fraction of a nanometer can give you a material that has a very dramatically different wavelength. So hence, we have, I would say, unlimited capabilities of having different wavelengths with the same material and tag different wavelengths, and we can see all those things in whatever applications we are using, right? So this is something that highlights the importance of the, yes, ma'am. Have a question?
I just wanted to confirm. So the example you gave of that tagging was from its biomedical imaging is done this similar way.
So wherever we are using, we'll have more examples. So the idea is that if you are tagging some system to look at specific wavelengths, these are the things that can do that for you. And you can adjust the size and you can use them in a mixture, and you can see exactly what would be the, if it's kind of a biological application like I was showing, but you'll see quantum dots are used in amazing ways, many different ways.
Yes, and it's very interesting topic. I chose it
Right.
for my assignment as well.
Yep. So now, where do we use fluorescence? Fluorescence is used in lots of biomedical applications. Fluorescence are molecules that we use to see reactions, see the bindings, right? So if you have heard the name Ahmed Zuwail, he was from Egypt, a Nobel laureate. He came up, he developed femtosecond laser, where we can now see the atomic reactions now. So that laser is so fast that it can see the states of atomic interactions. And we use lights for many of the bioreactions where we see molecules binding or not binding. And so we use fluorescence, which is a luminescence, a light emitting thing where electrons jump the band gap. So we see the difference of the levels as a form of emitted photon. So here they can do absorption of a broad spectrum and fluoresce or emit over a very narrow range of wavelengths. So that has a direct application in LEDs, right? For now, lasers, is a very specialized field in research where we are trying to use light for communication, optical communication. We are now talking about using fiber optic for our internet, right? Which means unlimited bandwidth. So that's where if you can use the same channel for same medium for millions of channels. Do you see the application? Which means now you can emit light with very fine difference in the wavelengths. And on the receiving side, you can capture that light and you know which channel is saying what. If anyone is from communication background, you can probably visualize what I'm saying here. So that's another application. Optical storage, where you have, we used to have CDs, then we had DVDs, then we got Blu-ray discs. Have you heard Blu-ray discs? Right? So have you seen a Blu-ray movie? So Blu-ray movies have very high resolution, very amazing, crisp picture. Why? Because we have put much more data on Blu-ray discs. Why it became enabled? Because now we have blue LED reading way to do that. So because we didn't have cheap blue LEDs. So blue laser allows for 35 times as much data storage than a conventional optical storage media. Why? Because we can make smaller spots on our CD. It's still the CD, but we have now smaller ones and zeros on that. Because now we have blue laser that can read those smaller zeros and ones, right? Digital storage, that's what we're talking about. So that's how we have become been able to cram much more data on those things.
And so they're a bit expensive too from ordinary, the Blu-rays movies.
So
The Blu-rays
expensive because they have to make money. But if you think about the cost of making the laser, probably still the same, right? So not dramatically different, but that's the what do you call it? Entertainment industry is there to make money, not to sell you things for how much they make it for. So, and if you look up, there are lots of videos on how you can make quantum dots. I just picked this up. I don't know what is the title, but if you look it up, how to make quantum dots, you'll find people have bunch of videos that they show. LEDs, the quantum LEDs, they're superior to standard LEDs because just like quantum dots are superior to bulk semiconductors in optical applications. So with the tuning of quantum dots, we can get very precise frequency of light, right? So which traditional LED cannot do. But with quantum dot based LEDs, we can have a very well-defined range of wavelengths that come out of that. And because it's small, the form factor can be made small as well. And this is why the cars are now coming with LED lights, right? So if you look around, even the traffic signals in many countries are now LEDs, LED based. So this is where now what you call QLED, quantum LEDs, they're replacing because they have low heat emission, which means less power, and they have full spectrum of light that we can use with them, right? Quantum computing, there are two groups who recently have shown that we can manipulate the data with quantum logic circuits. So they have come up with quantum logic circuits which use silicon quantum dots. Quantum computing historically has been done at very low temperature, right? So they have to cool down really well so you can control the spin, the state of the atoms. But with quantum dot, what they call quantum logic circuits, so they are using quantum dots to operate at a very significantly higher temperature than that, and which possibly would open doors for less expensive and more complex machines, right? So there are two groups who recently the report came out where they have tried to they have shown supercomputers which can do some basic manipulations. All right, so solar cells. So there's something that's known about quantum dots. They create two, even more multiple excitons, which means there are more electron hole pairs are being created per photon absorbed. So quantum dots are then allowing for the absorption of the light below the band gap without, with lesser voltage. So this is something which have recently been demonstrated in many applications where they are showing that the adjustment of quantum dots can be used to well define the absorption of the solar cell. So quantum dots, they emit up to 3 electrons for 1 photon of sunlight, which means now you have 3 times possibility of 3 times of absorbing the or available electrons that you can sweep out in the external circuit and store and do everything else. So this is something again that I mean shown, that the quantum efficiency then goes up because they can emit more electrons with that. All right, so this and just an example of cadmium selenide solar cell application. So they have done some change the volume percentage, and they have seen the power consumption. So there's lots of work is happening going on even right now in this area. So Muhammad Hamza saying, shouldn't it be 50% increase? Sorry, I missed where that comment came at. All right.